about a paper published this year, Giant Voltage Controlled Modulation of the Spinol Non-Oscillators Damping, Effective Damping. This paper published by these authors. And let's start with the usage areas of spinol non-oscillators. Spinol non-oscillators can be used in microwave signal generation, oscillator-based neuromorphic computing, combining nanoscale footprint, fast and ultra-wide microwave frequency tunability, CMOS, complementary metal oxide semiconductor compatibility. This differs SHNOs from spin transfer non-oscillators because spin transfer non-oscillators can't be compatible with the CMOS. Also, spinol non-oscillators can be used in strong nonlinear properties, providing robust large-scale mutual synchronization. Mechanism and advantages of spinol non-oscillators. In the left, you see magnetic tunnel junction or spin transfer non-oscillators. Spin transfer non-oscillators work with a spin current. You send the current to polarizer, and polarizer sends spin current to free layer, and it creates a natural frequency at the free layer, this spin current. And spinol non-oscillators use the spin orbit torque of the heavy metals. You send DC to the heavy metal. Due to its spin orbit torque, this DC splits into spin currents, spin polarized currents, and the spin polarized currents pass to ferromagnetic layer and creates a natural frequency, a precession frequency. In this photograph, you see JC, charge current, represents charge current, JS, spin current, ATT is the damping torque, and due to nature of the free layer or the ferromagnet. Spin transfer torque represents spin torque, and PR represents precession frequency. On the right, you see 4x4 a two-dimensional array of spin-hole non-oscillators synchronized, and this structure can be used as a for vowel recognition due to its synchronized nature. What's the motivation of this project? This project tries to create a way to individually control frequencies of the spinol non-oscillators in a big array or two-dimensional arrays, and individually control on-off states of the SANHOs in the two-dimensional or one-dimensional big arrays. Because to use these spinol non-oscillators in a neuromorphic computing, we need really complicated big arrays, but we cannot control the frequency, individual frequency and individual on-off states yet. We use voltage-controlled magnetic anisotropy to have this individual control over one spinol non-oscillator. In this photograph, you see the device schematic from microscope. These are the 4 contact paths. The up to used for apply the voltage difference. Voltage difference applied from top to bottom in this photograph. And this is the more zoomed in version. And this is the extra zoomed in version. And this bottom 2 contacts used for sending current. This current passes from the B-phase tungsten. B-phase tungsten known for its high spin orbit torque to create spin currents in the interface. And this axis represents Y upwards, X to the right, Z is out of plane. phi represents in-plane angle and theta represents the out-of-plane angle of the H. And also microwave signals measured from this bottom contact. Okay. And what's the voltage effect on the threshold current and auto-oscillation frequencies? These graphs show auto-oscillation frequencies versus sending current from the beta phase tungsten. This H is constant with these angles. Phi is the in-plane angle and theta is the out-of-plane angle. When we applied -2 volts, this graph happens, and 0 volts and +2 volts. And why this happens? They also made simulations to understand the nature of this phenomena, and from the simulations you can see that this is the spatial distribution of the linear modes represented with the normalized colors for each state, and this is for -3 volts and this is for +1 volt. You can see that this +1 volt situation is highly localized while this is less localized. They say that this change in the threshold current can be caused by this delocalization or high localization. And why they think like that? If we look at the D part, we can see that threshold currents change with voltage almost linearly, or linear fitted version. And they think this because this voltage change cannot affect the interface this much due to shielding of the coffee B layer. And so this effect must be caused by the affected part of the SHNO. So if this spatial distributions were too centralized, then affected part of the spin hole non-oscillator will be bigger because current flow in the SHNO only, and this part will be less affected from this effect. And also for the tunability of the frequency, we can see that when we change the voltage, there's a gap which we can get light or frequency, and this is almost 50 megahertz. So we can get 50 megahertz tunability with only 4 volts. This is it is 2 times the known gap for permalloy, other permalloy SHNOs, and we get almost 22% change in the threshold current. And if we use this formula to get how much frequency change, we get this graph, and it's almost 50 megahertz. Then they use FMR to get to understand the nature deeply, to understand this simulation and other effects caused by this threshold current change. And what is FMR? FMR is coupling between electromagnetic wave and magnetization, which medium it passes in. Decoupling induces a significant loss of power of wave. The power is absorbed by the precision magnetization of the matter, which is Larmor precision. And we have two types of FMR, which is used heavily. And this is VNA FMR, where you put a big magnetic field and an AC current and see the effect of this AC current in the magnetic field. When your AC current's power decreased deeply, it is the place where absorption is maximum. So it is the natural frequency of the Larmor precision. And on the right, you see the STFMR, where you send RF current to heavy metal to affect the ferromagnetic material under or up of it. We get a spin transfer torque due to heavy metal's nature, and this affects the, for example, coffee B layer, which is a ferromagnetic material, and we see a precision of its magnetization. So we get graphs like that, where we see absorption, and this alpha means the effective damping, not intrinsic, was effective. And they made these measurements in the paper, which I will explain now, with FMR. First, they made this measurement with fixed frequency. They applied different gate voltages and to see where these peaks happen. The Vmix represents the mixed voltage, which measured by the applied voltage, and also anisotropic magnetoresistance effect with changing current. It also adds something to the current voltage, so voltage drops or amplifies its value. And this measurement made by fixed angles, which is in plane 22 and out of plane 60 degrees. And they get these peaks almost at the same place, but slightly inclined line. So they used Kittel equation to get the change at the effective magnetization versus the applied voltage difference. When you change the voltage, it also changed the perpendicular magnetic anisotropy of the material. With fixed magnetic field, it will also change the frequency of the precision. And with different frequency, fixed H, you get different effective magnetizations. And this is the graph of this measurement. You can see that there is a almost 14% change at the effective magnetization. But if we think that this material's saturation magnetization is 1.3 Tesla, this change will be less than 1%. And this 1% change may create this much of difference in the effective damping and also at the frequency gaps here. And after this measurement, they also made measurements with changing frequencies, with changing magnetic fields. Each line represents another voltage difference. And you can see that if the magnetic anisotropy will be fixed, these lines must be parallel, but they aren't because of the changing magnetic anisotropy. And finding this line's slope and putting them in this theoretical formula will give us a change in the effective magnetization. And this effective magnetization will graphed in this part. You can see this blue dots represents the experimental measurements with the error bars, and red dots represents the simulation. But there's a tricky part here. Simulation gets the intrinsic damping constant due to its ability, but in the paper they say that the intrinsic damping may change due to voltage difference, but they cannot see it in the simulation. So these errors, not concentric circles, may be caused by the change in the intrinsic damping, they say. Okay. In the effective damping, you almost see a 42% change due to two things. First one is the change of the effective magnetization. And second one, just wait a minute. Oh, I couldn't find it, sorry. And second one due to a perpendicular magnetic anisotropy change. And they also get fixed frequency measurements with changing magnetic field and DC current in this time. This each line with different gate voltages represents the efficiency of the change, but they can see, you can see that they are not parallel, so efficiency will change again due to affected portion of the SHNO. And when the magnetization, when the voltage difference turns positive and increases, this affected area increases, as we can see from this simulation. And also this efficiency of the change increases as we wait from the simulation. We can see that. And how do they measure this? Now we can talk about the methodology behind that. How do they measure this frequency with the color bands? They measure it from the bottom contacts, as you can see from here. They send a DC current. Sorry. They send a DC current at fixed in plane angle with 22 degrees. This DC current signal amplified with LNA and finally put it into spectrum analyzer. And to measure this ones, they used RF current, which passed in from the beta phase of the tungsten. And this is the methodology behind the measurements. Now, they also discuss about these two questions. What causes the VCMA, voltage controlled magnetic anisotropy effect? And there's also two effects known in the literature, which cause this voltage controlled magnetic anisotropy. One is due to the band change in the coffee beam magnetic layer, which we used. 3D magnetic orbitals may change due to this voltage effect, and also Rashba effect may play a role, or DMI effect may play a role in this VCMA effect. And also, and second effect is bigger. Second effect is that if you can see, we put magnesium oxide at the top of the coffee bean layer. And if we apply a big voltage difference, and 4 volt is really big for our tiny device, its diameter is 150 nanometers. And this magnesium oxides layer, oxygens may immigrate to the coffee bean layer and may the ionic bands with this coffee bean layer stop. And this creates a much higher effect at the threshold current. Also change the energy of the coffee bean layer, which we can measure. And what causes the effect in our project? They say that due to small changes which they calculated, this caused by the band effects of the coffee bean layer. If it was the ionic effect of the oxygen immigration, it will be 3 times higher. This decreases will be 3 times higher if it was the ionic effect. And how can we improve spin hole nano oscillators? We can improve them with the device architecture. If we place this measurements contact in a different way, or made our device synchronized with another one, this may be affect our spin hole nano oscillators performance. And also we can use the ionic effect at our spin hole nano oscillator to much higher change in our device. And output of this device must be amplified to use them in the CMOS because this outputs of the spin hole nano oscillators before the amplifier was really small to use them in a CMOS compared to the STNOs. And this is the last thing they said. And I also added some useful links. This one is an instructive video about STNOs and their implementation in the nanomorphic computing from Purdue University. And this article explains the spin torque ferromagnetic resonance by calculations or experimental data. This is the vowel recognition article, which they used for synchronized spin hole nano oscillators in a way that recognize one woman's voice in 37 women. And this article contains the photograph which I showed you. They worked on a two-dimensional arrays and one-dimensional really big arrays to see how many spin hole nano oscillators they can synchronize. And this is it. Thank you for your attention.